Dassow, and I'm going to present my work on the package number 3. So what is our work package going to do? We want to assess the potential of mine shafts for heat storage. So basically, we want to answer these questions. How fast can we heat up the shaft? And this will be especially interesting for our upcoming pilot study. And how quickly does the shaft lose this heat? What does thermocyclic heating and cooling do to the heat storage? And how much detail does our model have to answer these questions? So as mentioned before, we'll run a pilot soon. And for example, for our model, we need to make some first decisions here. Like, what is the heat source and how do we implement that? And for our for this model that I'm presenting, we have to make a few assumptions, like the heat storage coefficient. Here it's H, which is assumed to be constant. So from that, we build up our first model, which couples the turbulent flow in the shaft with the heat transfer over the area. So this includes the rock and the shaft and its lining, and all the modeling is done in COMSOL. And for the turbulent flow, we use a Reynolds average Navier-Stokes model. So this is a bit of a busy slide, but it's just if you're interested in the model setup. We need to make, we need to set the initial and boundary conditions, and most of them are from literature values or calculated or from smaller models, because as we learned from other presentations, often data aren't available. So for our model, we assume a homogeneous rock, which you can see in yellow on the left, and the water body is in blue. And this is sort of a slice of a cylinder. So it's a radial symmetric approach to save some computing time. So basically what we get out of this is a 3D representation. So this will form a cylinder later on. Oh yeah, and the heat source we're going to use is an implemented heat flux boundary, which will sit 50 meters below the surface as a sort of line heat source. And for this setup, we only model 14 days to see how fast we heat up the shaft. So let's have a look how the shaft heats up. On the left, you can see the temperature slowly increasing. The hot water is rising to the top, so you can see the hotter surface. On the right is the velocity field in white as the little streamlines. They show the direction of the flow. And the color bar is the velocity magnitude, so you can see how fast the water flows. And you can see how the water along the heat source is quickly flowing up, heating up to the surface and cooling down on the surface and flowing down on the cold walls of the shaft. So after 14 days, this is the same figure as before, basically not a video now anymore. We can look at the average temperature of these top 50 meters of the water. And you can see on the right that we probably, with the assumptions we made in our model, we will heat up the shaft by 20 degrees. And we can also let the whole system cool down. If we turn off our heat source, then you can see in green how the cooling down is happening. So we lose around 5 degrees in those 14 days. So much slower than our heating up, which is what we want, ideally. We have other models, for example, this one, which shows the groundwater flow coupled to the heat transfer. So for this model, we ignore the fluid dynamics, but ultimately we want to couple all of it into one big model. And we need to do a lot of sensitivity studies on that. For example, the dip or width, how is that influencing our heat storage? And I'll present a quick example on the shaft lining thickness influencing the heat distribution in the model. So for this one, we have a 3D setup now, and we introduce a hydraulic gradient, which we didn't have before, and a constant wall temperature of 40 degrees as our heat source. And now we look at 50 days. And what you can see here is how the groundwater velocity carries the heat away. So on the left, you can see the groundwater flow changing around the cylinder structure of the shaft. This is an upwards view of the model we just saw. And on the right, you can see the temperature sort of smearing in the direction of the groundwater flow. And if we now take a slice of that and look sort of in the middle or anywhere else in any depth, what that does to the local temperature distribution, you can see that the shaft lining influences this temperature actually a lot. So if we assume we don't have any lining in our model, then we get almost a 10 degrees difference to the 1 meter lining. But probably our shaft will have a lining between 0.5 and 1 meter. So we are probably around a difference of 5 degrees locally for this example. So to summarize this, we had a quick look at 14 days of heating, and we also had a look at 14 days of cooling, which is much slower. And for our model, for a quick sensitivity study, we showed that the lining is quite important to be included in our whole model. That's it.